So good morning, class. You are welcome to today's lecture. We are very sorry for the technical hitch we had on Monday. Hopefully, we are going to have a better lecture today. Please, if you can hear me, just put it on the group chat. Just put it on the group chat if you can hear me. Okay. So you can hear me. So today we are going to be looking at thermochemistry. So for thermochemistry, we are going to look at what thermochemistry is, and we also look at some simple calculations based on Hess law. So what is the scope of our discussion? We have introduction, systems and surroundings, energy, work, heat, internal energy, first law of thermodynamics. So we start with a brief introduction. So what is thermochemistry? We said thermochemistry is a branch of chemistry that deals with the study of heat energy. And this heat energy can be in form of chemical reactions. It can also be in form of phase changes. What are some of the phase changes we know? We have melting, we have boiling. We also have, of course, if you have your water, you boil it, it will go into boiling, and from boiling, it can go into vaporization. So thermochemistry, because it has to do with heat change, and this heat change, because we are looking at chemistry, so it's usually associated with chemical reactions, including phase changes such as melting and boiling point. And also, because it has to do with heat energy, it has to do with a system and the surrounding, because the exchange has to be between a system and the surrounding. And what is the essence of this heat energy? You can actually use this heat energy to predict reactants and products. Aside using it to predict reactants and products, you can also use it to predict if a reaction will be spontaneous or non-spontaneous. What do we mean by spontaneous and non-spontaneous? Spontaneous meaning that this reaction can occur without external stimulus. So what it means is that you don't need heat or pressure to actually make this reaction to occur. So that is what we mean by spontaneous. You don't need any external stimulus. Why for non-spontaneous, you need an external stimulus. Now, we have already define thermochemistry as a branch of chemistry that deals with the study of heat energy. We also say that thermochemistry is also a branch of thermodynamics. So here we are giving two definitions: a branch of chemistry. Not only is it a branch of chemistry, it's a branch of chemistry that deals with the study of heat energy. And that is why we also say that thermochemistry is also a branch of thermodynamics, because thermodynamics have to do with heat change. So those are the two definitions we are giving here as thermochemistry. So we are bringing in thermodynamics because it has to do with heat energy. Because the word thermal has to do with heat. So that is why we also say that thermochemistry is also a branch of thermodynamics. And of course, we've also talked about it has to do with the change from one form to another. And this change can be in form of heat associated with chemical reactions. And because we are talking about heat energy, so we are actually looking at energy here. But the energy we are talking about has to do with heat. So that is why we say that energy is the capability to do work. And what are the forms of energy we are going to be looking at? We are going to be looking at heat energy. We are going to look at mechanical energy. We are also going to look at chemical energy. So let's look at some definitions that is associated with thermodynamics or heat energy. So the first is a system. What is a system? A system is the specific part of the universe that is being studied. And this system can be made up of, it can be a living thing or it can be a non-living thing. And that is why you can decide to study a cell. You can, most of you all are almost doing biology. So you can decide to study a cell. If you decide to study a cell, then that cell is the system you have decided to study. You can decide to study a city like Lagos. You have decided to study that system. So here, in this conical flask, we have a system here. So if we decide to study this system, this is a system that has a solution of barium hydroxide and ammonium nitrates. And this system has surrounding. What do you mean by surrounding? That is everything that is outside the system is considered the surrounding. And between the surrounding and the system, we have what we call a boundary. So the system is separated from the surrounding by a boundary. So this is your system. This is your surroundings. The surroundings, of course, is outside the system. Then the boundary between the surrounding and the system, this is your boundary. So now we've defined what a system is. What are the kind of systems that can be studied? A system may be isolated, a system can be closed, and a system can be open. When we say a system is isolated, from the word isolated, that means that when you say somebody is isolated, that person decides to stay on his or her own. So when we say an isolated system, this is when there's no exchange of energy or matter with the surrounding. So that is how we describe an isolated system, because it has to do with exchange of energy or matter with the surrounding. When there's no exchange, then that is what we call an isolated system. A good example is your gas in a cylinder, the gas we use at home to cook. That gas is enclosed in that cylinder. There's no exchange of energy or matter with the surroundings. So that is what we call an isolated system. No exchange of whatsoever between there's no exchange between the surrounding or matter. Of course, we know that matter is anything that has weight and occupies space. Now, when we talk about a closed system, what do we mean? The word closed. We use the closed system when there's exchange of energy, but not matter with the surrounding. There's exchange of energy, but not matter with the surroundings. And a good example is your air conditioner. So your air conditioner, of course, if you're in a system, of course, it's a closed system. So there's exchange of hot air and cool air, but not matter. So there's only exchange of energy with the surrounding, but not matter. And another good example is your radiator engine in your bonnet. So there's exchange of energy. Of course, your radiator cools the engine. So there's exchange of energy, but not matter. Now, the other one we have is your open system. What do we mean by open system? From the word open, that means anything is possible. So when there's exchange, both matter and energy with the surrounding, that is what we call an open system. So when it can exchange both matter and energy with the surrounding. And a good example is your pot of boiling water. Your pot of boiling water, of course, when you heat up the water, there's exchange of matter. Matter is anything that has weight and occupies space. And there's also exchange of energy with the surrounding. Of course, the water boils and goes into vapor. So there's exchange of both matter and energy. So that is how we define the different types of systems: isolated, closed, and open system. Now, here we have a system. The system we have here is a reaction between solution of your barium hydroxide, solution of your barium hydroxide and your ammonium nitrate. Of course, these are the surroundings, and we have a boundary. Now, looking at this system, this reaction, what kind of system do we think we have here? Is it isolated? Is it closed? Or is it an open system? Please, can you type your answer in the chat? I want to see your answers in the chat. Can you do that? So let's type our answers into the chat room. Thank you very much for your answers. So at least I'm sure you can hear me. Sorry about that. So we've talked about the system. So we look at energy. What is energy? Energy is generally defined as the capacity to do work or to transfer heat. And we are going to look at about 4 types of energy here. But first of all, we look at the kinetic and the potential energy. So the kinetic energy is energy possessed by an object in motion, and it's usually called energy in motion. That means when we say energy in motion, we can see this tractor is dissipating kinetic energy, because we say it's the energy possessed by an object in motion, and it's usually called energy in motion. So that is our kinetic energy. And your kinetic energy depends on mass and velocity of the object. Now, I'm going to ask you a question. If you have a tractor and you have a bicycle, which of them do you think will perform more work? Knowing in mind that your kinetic energy has the formula T is equal to half mv squared. So what it means is that your mass is very, very important, and velocity. Your mass and your velocity will actually affect the kinetic energy. So the one that has a higher mass will always have a higher kinetic energy than the one that has a lower mass. So invariably, the one that has a higher mass, which is your tractor, will be able to do greater work. And that is why most times, if you want to do more work, especially in the farm, you see that people use their tractor than the hoe. So because of the mass, because the mass will actually affect the kinetic energy. So your mass will affect your kinetic energy and also the velocity. Aside that, also even temperature also. Temperature will also affect your kinetic energy because we are looking at internal motion, and this internal motion can be in form of vibration, it can be in form of rotation. Of course, if there's increase in temperature, we expect the vibration or the rotation to be more. So invariably, your temperature can also affect your kinetic energy. So we look at our potential energy. What is potential energy? Is the energy possessed by the object as a result of its state or position relative to other objects. I will also say your potential energy is difference. There has to be a difference. Why do I, before I give this explanation, we have this ball here, it's on the ground state, and we have the ball being suspended up. So if you look at what I have here, I say ball has no potential energy. Why this other ball has potential energy? Because there is a difference between the energy of an object in a given position and its energy at a reference position. So there must be a difference. And again, your potential energy is usually, the formula will normally, because it's usually affected by your gravitational force, that is acceleration due to gravity. So for your kinetic energy, we say it's half mv squared. For your potential energy is mgh. Your m is the mass, the g is the acceleration due to gravity, while your h is the height. So you see here, there has to be a difference in position for you to be able to calculate your potential energy. And again, we say it's a stored, because the energy is stored. It's a stored energy. So, but in chemistry, the most important potential energy to us is what we call electrostatic potential. Electrostatic potential because it has to do with charged particles. Of course, when we are looking at reactions, we are looking at particles, we are looking at electrons. So for us, we are more interested in interactions between charged particles. So what it means is that we are looking at measuring the strength of the charged particles from one point to another, because they are going to be at different positions. So we've looked at kinetic energy and we've looked at potential energy. These are those two we are going to carry out calculations using either your kinetic energy or your potential energy, because I've given you the formulas. So your kinetic energy is your half mv squared. As I said, it depends on the mass, the velocity, and the temperature. For your potential energy, that depends on the mass. You have to know the mass, the acceleration due to gravity, and the height. So aside those two, which is common, which of course I know is common because you've looked, maybe in your secondary school, you looked at those using those equations. We also have our radiant energy. From the word radiant, we know it has to do with our solar energy. So it's solar energy, and this comes from the sun. And the primary source of this energy is from the earth. And what happens is that this heat or this radiant energy normally heats up the atmosphere and also the earth we live in. So the sun we are getting is actually our radiant energy. And it's also another importance of our radiant energy, aside heating up the atmosphere and the earth, we also use this. It's also very important in vegetation. One good example is making in photosynthesis. So we also have the chemical energy. This is a stored energy within the chemical substances. Because we say it's a stored energy, so we also say it's a kind of potential energy, because your potential energy is a stored energy. So your chemical energy is also a kind of potential energy. And when do we talk about chemical energy? When the substances, when they participate in chemical reactions. Of course, when they participate in chemical reactions, we expect energy to be released. Energy can be stored, or it can be converted from one form to another. Now, we've been talking about energy. Kinetic energy, potential energy, radiant energy, chemical energy. What is the unit of this energy? The unit for energy is joule. Joule is a name of a person. That was the person that investigated work and heat, because the unit for work and heat is actually the joule. So the man, which is James Joule, he was the one that investigated work and heat. Not only that he was the man, what it means that he's the first person that investigated work and heat. Just as I am now, Dr. J, if I'm the first person that investigated anything, I would definitely put my name as the, so that's whatever I've investigated, that will bear my name. So whenever you're studying that topic, or that whatever it is, that my name will always come up. So your joule is the name of the person that first investigated your work and heat, because that is the unit of work and heat. And 1 joule is what? 1 kilogram meter second. And another common name for your joule is your calorie, or what we call carb. So how do we define a calorie? A calorie is defined as the amount of energy required to raise the temperature of water from 14.5 degrees to 15.5 degrees Celsius. So there's one unit, it's 1 unit, because between 14.5 to 15.5 degrees Celsius is 1 unit. So a calorie is defined as the amount of energy required to raise the temperature of water from 14.5 degrees to 15.5 degrees Celsius. So that is your calorie. So the unit can be in joule, or it can be in a calorie. So we've talked about kinetic. So let's look at some calculations. Based on what we have studied. So the first one, we are going to look at kinetic energy. So it says a person weighing 75 kilograms or 165 pounds runs a course at 1.78 meters per second. What is the person's kinetic energy? So what is the formula we are going to use? I would have asked you to unmute yourself, but no problem. So I know you know that. So we are going to use our half mv squared, because we are looking at kinetic energy, where m is the mass, v is the velocity. So our mass here we've been given as 75 kilogram, and the velocity is 1.78. So you will all agree with me that this is a very simple calculation. So we have our kinetic energy, half mv squared. So the mass is 75 kilograms and the velocity is 1.78 meters per second. Of course, why we squared that? Because our velocity is squared. So if you carry out that calculation, and I will expect you to do that, when you get home, use your calculator and carry out that calculation, we are going to have 119 joule. So why are we having it in joule? Because we said that 1 joule is kilogram meter per second. That is the unit of our joule. That is it. One joule is 1 kilogram per 1 kilogram meter. This is per second. So that is why we have the unit as joule. So the second we are going to look at, because I told you, I gave you 2 equations, kinetic energy and potential energy. So for your potential energy, the question says, what is the potential energy of a 1,360 kilogram automobile packed on the top? So your potential energy, we must know that we have to know the height because it's your MGH. Parked on the top level of a parking garage. So the height is what? 36.6 meters. That is about 120 feet high. So our formula is your MGH. You also agree with me, this is another simple calculation. You are given the mass, your gravitational, your acceleration due to gravity is your 9.86 meters per second. And the height we are already given as 36.6 meters. So calculating your potential energy, you just do the calculation there, which is your MGH. And that will give you, of course, your mass is in kilogram, meter per second. So what is that unit? Joule. So you are going to have it as a joule. So you have 48810.456 joule. So we also look at another one, electrostatic potential, because I told you that for the potential energy, we are more interested in the electrostatic potential because that has to do with chemical reactions where we have charged particles. So the question says, find the distance between two spheres of charges, having 0.003 coulomb and minus 0.001 coulomb respectively, if the electrostatic potential energy is minus 450 joule. So that is your what? Your potential energy. So we have, so the formula, so we have our electrostatic potential. This is our electrostatic potential is equal to your K. Your K is actually what? Your Coulombic constant. It's a Coulombic constant. Because it's a constant, you'll be given the value 8.99 times 10 raised to the power 9 joule meter per coulomb. And the Q1 and your Q2 are what? The distance, the electric potential between the two charges. Your Q1, your Q2. While the R is the distance between the charges. Your Q1 and your Q2 are the electric potential, the potential between the two charges, while the R is the distance between the charges. So using, and what are we calculating? We are asked to calculate the distance between both. So the distance is actually going to be what? The R. The R is now your distance. So if we do that equation, we are going to have our R, because if you cross multiply, your R will now be your K, Q1, Q2 all over your electrostatic potential. We are given our K, which is a constant. We are given the distance, our Q1 and our Q2, and also we are given the electrostatic potential. So if you do that calculation, which I have tried to bring out, which I tried to do, so that we don't just look at the answer, you must know how to carry out your calculations. So as I said, this is our electrostatic potential. This is our constant Q1, Q2 over R. So what we have here is our minus 450 joule is equals to our K multiplied by our Q1 multiplied by our Q2 all over R. So if we do our cross multiplication, we now have a minus 450 joule R is equals to our Q1 is equals to our K, Q1 and then Q2. So making R the subject of the formula, we now have a 8.99 times 10 raised to the power 9 joule meter per coulomb times our Q1, Q2 over 450 joule. If you notice, the negative is no longer there because this is supposed to be negative. We have a negative sign here and we have a negative sign here. So the negative sign here will cancel off the negative sign here. So that is why the negative sign is no more. So our distance is now going to be 0.599 meters. Okay, yeah. That is how we got our 0.99 meters. So that is the first lecture, but we still have some time. So let's look at our second lecture. Our second lecture, we just look at a few slides and we'll be done. Before we go to that, do we have any questions? Or we'll ask the question at the end of the class so that we'll just continue. But I hope you can still hear me. So work. What is work? So work is the energy used to cause an object with mass to move through a distance against a force. So work is, the formula we have is your force multiplied by distance. And the most common type of work encountered in chemistry is the work that has to do with your pressure volume. So most times the calculations you are going to be involved in has to do with your pressure and the change in volume. And the negative sign there is only showing us that work is being done. That is the essence of the negative sign. So where your P is the pressure acting on the system, while your change in volume is your dV. Sorry. I just want to be sure that you can hear me. Sorry. So let's look at one example. So I always like when I teach, we look at example because I know that students, most times calculations is always a little bit difficult. So when I teach, when I introduce the topic and it has to do with calculations, we look at some calculations. So let's look at work. So it says calculate the work associated with the expansion of a gas from 46 liter to 64 liter at a constant external pressure of 15 atmosphere. So as I said, for us, the most common work in chemistry that we encounter has to do with pressure and the volume. So that is why we have the equation work is equals to minus P delta V. So the formula we are going to use is work is equals to minus pressure multiplied by change in volume. And our pressure we have been given as 15 atmosphere. Usually, because we say that work, energy, the units is usually in joule. So we have to convert your pressure that is in atmosphere to par. The unit of pressure is par. If you have to get the unit of your work in joule. So you are first of all, except the pressure is given in par, PA, that is par. If the pressure is not given in par, if it's given in atmosphere, then you must convert it to par. And the unit of conversion is 101,325. That is how you convert your atmosphere to par. So the first thing we are going to do here is to convert our pressure from atmosphere to par. So we multiply the 15 by this factor. And once that is done, then you can now multiply by the change in volume. And the change in volume is from 46 liter to 64 liter. So that will give us the work in joule. So your per liter is actually your joule. So that is how you calculate the work, and your unit has to be in joule. So look at heat. What is heat? Heat is the energy that causes a change in the temperature of a system. So what it means is that for you to be able to explain heat very well, you must be able to have a difference in temperature. Because to say it's the energy that causes a change in the temperature of a system. For there to be a change in temperature of a system, that means there has to be a flow of heat from maybe a low temperature to a high temperature. So there's usually a transfer. So the heat is the transfer of thermal energy between two bodies that are different temperature. And heat usually flow from a higher temperature to a higher temperature. And that is why if you are very hot and you enter into a system that is cool, maybe an air conditioner room, you see that, so what it is that the heat from your body is going to flow into that system. And when your body acclimatizes, when the temperature is equal, then the heat flow stops. So heat will always flow from a higher temperature to a lower temperature. And as I also told you, your work and your heat, because they are forms of energy, they will have the same unit of energy. And that was why the calculation we did, we had to change our atmosphere to power so that the unit of the work will be in a joule. Now we've talked about heat. Now, we have other definitions we have to look at considering heat. We have what we call heat capacity. We have what we call specific heat capacity. We also have what we call molar heat capacity. First of all, what is heat capacity? From the word capacity, that means it's amount. Whenever you look at a word, always first of all look at the English. Know the English definition of that word. So we say that the heat capacity is the amount, and that was why I put it in red. Is defined as the amount of heat required to raise a mass of the substance by 1 degree. When we looked at a joule, we saw that it was from 14.5 degrees to 15.5 degrees Celsius. That is a difference of 1 unit. So your heat capacity is the amount of heat required to raise a mass of the substance. So what it means is that you have to heat. So mathematically, our heat capacity is our Q over delta T, where your Q is the heat absorbed, and your T, delta T, is the difference in temperature. And the unit, as I showed you, will always be in joule, because it's going to be in joule per Kelvin or joule per degree Celsius. So that is your specific heat capacity. That is your heat capacity, sorry. So we also have specific heat capacity, which is your CS. So now we are being more specific. The first one was just heat capacity. It's just the amount of heat required. Now we are saying specific. So now we have to be specific. What is the amount of mass we need to raise? We need to raise what? 1 gram of the substance. So your specific heat capacity, which is your CS, the S here is specific. For your heat capacity, we only use a C. But specific heat capacity, you have your CS, subscript S, is the amount of heat required to raise. Now we have to be specific because the word says specific heat capacity. To raise 1 gram of the substance through 1 degree Celsius. Yeah. So now we just add M, and the mass has to be in gram or kilogram. So that is why here we now have Q over M delta T. So here we're adding mass because they've already told us that it has to raise 1 gram or 1 kilogram. So the unit now is now going to be joule per kilogram or joule per kilogram per degree Celsius. Why this is joule per kilogram per Kelvin. Of course, most times if you are given in a Kelvin, you have to convert to Celsius. Now that is for your specific heat capacity. What about our molar heat capacity? So we are introducing more terms. So molar has to do with a mole. So instead of raising 1 gram or 1 kilogram this time around, we are going to raise 1 mole. So always know be specific what you are going to use. Is it going to be just the amount? Are we asking just for 1 gram? Are we asking for 1 mole? So your molar heat capacity is the amount of heat required to raise 1 mole of the substance to 1 degree Celsius. So now, instead of having the mass in gram or kilogram, we are now having it as a mole. So what it means is that you must know the number of moles to be able to carry out calculations using your molar heat capacity. So the unit is now going to be in joule per mole per Kelvin or joule per mole per degree Celsius. So let's look at one calculation, sorry. So here we say calculate the heat absorbed by 15 grams of water to raise its temperature from 20 degrees Celsius to 50 degrees Celsius at constant pressure. So from this, we already know the equation we are going to use because we are given gram. So we are going to use the one that has mass. So what it means is that I would have asked you the question before I went there. So because we are calculating, they've given us the mass, what it means what we are calculating is our specific heat capacity. If we had been given mole, what formula are we going to use? We are going to use your molar heat capacity. So what I want you to understand is that because we have been given the heat absorbed in gram, invariably, that tells us that we are going to use your specific heat capacity equation. And our specific heat capacity is our Q, the heat absorbed, over your mass, which is in your gram, multiplied by your change in temperature, which is your delta T. So the heat absorbed, which is your Q, is going to be your specific heat capacity, your mass multiplied by your delta C. And we are giving the specific heat of the water as 4.18. Again, your formula is going to be in a joule because we are calculating the heat absorbed. Okay. So we stop there for today. Any questions? Any questions? So at least we are happy that everything worked fine today. Please let me know. Did everything work well? Put it on the group chat. I will give you the slide. Don't worry, and it's being recorded. I just want to know if everything worked well today. Okay? Okay, you are happy? Okay, thank you very much. So we hope on Friday it will even work better. So before the end of today, I'm going to post the slides to your platform and also the recorded version. So you have a question, put it on the group chat. She says, when we say heat flows from a hot object to a cold object, is it just a convention or something that has been scientifically proven? It has been scientifically proven that heat flows from a from a hot region to a cold region. This one says, why does the answer not have a negative side in the previous slide, ma? The previous slide. I hope it's not the one that I think I explained that the negative will cancel the negative, and that was why there was no negative. I want to assume that that was the question you asked. Where the negative, that's when we were calculating the minus 450 joule and the Coulombic charges. You know, we had negative. So I told you the negative will cancel the negative. And that was why that 0.599 did not have any negative sign. I want to assume that that was the question you were asking. He said, how did the 10 raised to power 3 come about? He said, Mark, in the case of heat flow from a hot region, heat flows from a hot region to a cold, because the one that is hot, the one that is cold, it has to flow from a hot region to a cold region. So you multiply your, please, that conversion from pressure to power, I didn't understand that part, as it is a constant. That value is a constant. So because you are given the formula is in atmosphere, I say your pressure, because you want to get it in joule, you have to convert your atmosphere to bar. And that value is a constant. So whatever value you are given, you must, if it's given in atmosphere, except that value is given in bar. If it's given in bar, then use it direct. But if it's given in an atmosphere, you have to convert it to bar and you use that value. Based on the work formula, how was 18 liter converted to in the example under work? Let me see. It was just example under work. Okay, let me share the slide so that I can understand what you're saying. So 46 liter to 64 liters. So what are you talking about? Okay, this, yes, we are not, it's not meant to be there. So your answer is 27357 joule. If you multiply 15 times, minus 15 times 101325 times 18, this will give you this. Okay. So I'm going to send the slide. Gram to kilogram. The constant value to change, we said, what is the constant value to change from atmosphere to par? I think I gave you the value. That is about, I think 101325. 101325. Okay. So I'll see you on Friday. Thank you very much. Oh, we say H plus blah, 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 blah. We said, please, ma, what time is it? What is your question? What time is what? Our lecture on Friday is 9 to 10 too. Our lecture on Friday is also 9 to 10. One is our test holding. I can't say that for now. So I'll see you on Friday.